Hi scholars, I hope that you and your family and loved ones are doing well. We at SEO are thinking about you every day, we care about you, and we're sending our best wishes. So usually in an SEO math class, we all rely heavily on your knowledge, your thoughts, and the ideas that you bring into the classroom. And there are many opportunities for you to talk with your classmates about an idea or to come to the board, to share what you're thinking, to ask questions, and just in general to solve problems together. And so although much of these activities aren't possible when you're watching a video, I still encourage you to try to watch this video as if you were in a classroom actively. And so what this means is to take out your workbook or a notebook while we go through the lesson together and take notes in it, just as if you were in a classroom. Feel free to pause, rewind, and watch parts of the video a second time if you're confused. And make a note of things that you're still confused about after this lesson so that you can ask your instructor. All right, sounds good. So let's get to it. During the last lesson, we discussed the distributive property, and today we're going to build on that idea. We're going to talk a little bit about factoring and divisibility and the relationship between factoring and divisibility. Before we begin, up to this point, we've been using this the x as a multiplication sign, so we've been saying things like 2 times 3 equals 6, and we're going to shy away from that from this lesson forward, and we're going to instead write multiplication using the parentheses. So we could say 2 times 3 is 6. We'd write it something like this: 2 times 3 is 6. And this is because in this lesson and future lessons we're going to be using more algebra. We're going to be using the variable x, right, as a variable. And so we don't want to confuse this x right here, which means multiplication, with this x, which is a variable. So just to give you a heads up, we're going to be using parentheses to mean multiplication. Okay, so let's begin. As a starting place, let's look at the definition of what does it mean to factor. So factoring is the process of rewriting a number or an expression as a product. Okay, and a product means two or more things that are being multiplied by each other. We'll see an example of this. A factor is one of the parts of this product. And the big idea in this lesson is that factoring undoes or reverses multiplication. So it's sort of like we can factor in one direction and we can reverse it by multiplying. So let's see what this looks like. We're asked to write an example of factoring a number. So there are many different ways that we can factor a number. Let's take the number 30, right? And one way to do it is we could think about like a factor tree. Remember when you said 30 is what times what? Well, we said 30 could be 2 times 15, and then you sort of get it down to all its prime factors, right? And 15 is 3 times 5, and so we can say that 30 is really 2 times 3 times 5, right? So we could express 30 as 2 times 3 times 5, and this would be an example of factoring the number because we took that number 30 and we rewrote it as a product, right? We rewrote it as a product of 2, 3, and 5, so that is correct. That is one way to factor 30. Are there other ways to factor 30? Sure, right? Once we have the prime factors, so here we have our 3 prime factors, we can actually take combinations of these factors. And so what do I mean by that? Well, I mean, I could also write 30 as, if I wanted to, instead of 2 times 3 times 5, what is 2 times 3, right? Which is 6. I could also write it as 6 times what's left over is 5, right? That's another way to factor it. I'm still rewriting this number as a product, so that still works. I could take another combination, right? I could do, instead of 6 times 5, I could rewrite this as, here I'll just use the same color, I could rewrite this as 10 times 3. And again, we say this 10, where did that come from? Well, the 10 is just, right, 5 times 2 here, right? So we in this case, we took this combination of these factors, and the 3 was left over as well. So this is an example of how we can sort of do a lot of factoring. Let's do an example of factoring an expression now. So there are many different possibilities. So let's take the expression 2x plus 8, for example, and we can factor this. We can say, well, this 2x is really 2 times x, and this 8, does it have either a 2 or an x in it? It sure does, right? This is a 2 times 4, and we have our addition here, and so we say, okay, so They both share a common factor of 2, right? And so we can factor that 2 out. I'll put it in red. So here's the 2. Here's our common factor of 2. And then I say, okay, 2 times, well, what's left over? Parentheses, again, mean multiplication. And what's left over is our x plus 4. So I'm just going to write that in, x plus 4. And this is one way to factor 2x, or this is a way to factor 2x plus 8. And remember what I said up here about how factoring undoes or reverses multiplication, right? We could use, if we wanted to, we could use the distributive property here, right? 2x plus 8 to get back to where we started. So if I go from here to here, right, this is multiplying, right? This is multiplying. And if I go from here to here, this is an example of factoring. And so here we see how they're sort of like inverses of each other. One of them sort of undoes another. Okay, let's keep going. Example number 1, factor the sum 12 plus 21 by finding a common factor. So we're going to do this fairly quickly. 12 I can rewrite as 3 times 4, right? We agree that 12 is 3 times 4. 21 I can rewrite as 3 times 7. Again, we're just rewriting it in a different form to expose the fact that we have a common factor of 3 right here. So we're going to say all this equals, I'm just going to write it over here a little bit bigger, that common factor of 3 times what's left over. Well, I have a 4, right, plus a 7. So 3 times 4 plus 7. And there we are. This is how we factor it. And again, this is this idea that factoring, right, is sort of going in this direction, and multiplying or using the distributive property is going in this direction. So we're reversing, we're undoing, doing and undoing these things. So right here we can see what this factoring looks like within the context of an area model. Here I have my 3 times 4, 3 circles by 4 circles. Here I have my 3 times 7, right? And the sum, 12 plus 21, right, is exactly the same when you factor it, right? It's 3 times 4 plus 3 times 7, otherwise known as 3 times 11, right, or 33. Now, of course, 12 plus 21 does equal 33. So this is just another model, another way that we can interpret this very simple sum or addition problem. And again, you might ask yourself, so what, right? This is the big question. And the answer is, yeah, in this particular example, so what? It doesn't really mean anything. We're going to be factoring expressions. We're going to be learning how to factor quadratic expressions, higher degree polynomial expressions, and all of the work and all of what we're going to learn about how to manipulate these algebraic expressions. Some of them can be a little bit difficult, a little bit challenging. It all comes down to this basic idea of factoring, right? Factoring is rewriting something as a product of 3 and 4 plus 7, right? This is a product of one thing times another thing. Notice the sum here, there's no product here, right? This is a 12 plus 21. This is a sum. This is not a product. So that's the big idea of factoring, rewriting as a product. Let's keep going. In addition to being able to deal with more complicated algebraic expressions and use factoring to rewrite them as products, factoring can also be used to make and justify mathematical arguments. And another word for justifying a mathematical argument, for showing that a pattern is always true, another word for that is proof. Okay, and so for the rest of the lesson, we're going to sort of take what we know about factoring, and we're going to see how we can sort of use that to prove that some statements are always true. Okay, so we're going to start here with this idea of numbers being divisible. So if I have the question, what is 12 divided by 4? Well, 3, right? So we can do that. We know it's 3. We can put it in the calculator if we want. 12 divided by 4 is 3. So take a minute and say, if you wanted to sort of justify that, right? So this is this word justify. So it means make an argument, right? So sort of argue that 12 divided by 4 is 3, right? If someone said, I don't believe you, can you show it to me, right? How would you do it? So how do you know that this is true? So take a minute and think about that. Okay, and so we can actually justify this using factoring, right? So if I say 12 divided by 4, one way that I can rewrite divided by, right? And we're gonna do this in a couple lessons as well, right? I can write it sort of using this fraction bar, right? 12 divided by 4. Okay. Well, 12, can I factor 12? Sure I can, right? 12 is nothing more than 4 times 3. I'm rewriting 12 as a product. And 4, I can just keep it down here. If I want it to be fancy, I could rewrite 4 as 4 times 1, right? Because anything times 1 is just itself. Or you could just leave the 4 down there, right? So this 12 divided by 4 is really 4 times 3 divided by 4 times 1. And I'll be darned if you don't have the same factor, right, on the top and the bottom, on both the numerator and the denominator of this particular fraction. And so if that's the case, you can cancel these out, right? And you can rewrite, so you can cancel them out and you can rewrite this all together as whatever's left over, which in this case, right, is 3 times 1. Okay? If you're feeling a little uncomfortable about canceling them out, you can also reason that these 4's right here, if I just take a look at just this part of our fraction, 4 over 4, I'm just going to write it over here, 4 over 4. What is 4 divided by 4, right? That's just 1, right? Anything in general, anything, x divided by x is always going to equal 1, right? If I have 4 candy bars, I have 4 friends, I give each friend a candy bar, everyone gets 1 candy bar. So this is another way to sort of reason with why 12 divided by 4 is equal to 3. So there's our 3 right there. There's the 3 that we had in our initial answer. So the question is 12 divisible by 4? Yes, right? And so what does it mean to be divisible? It means that you can, when you divide 12 by 4, you get another whole number. You get another natural number, or you could get another integer if we're dealing with negative numbers. That's fine. But what it means to be divisible is that 12 divided by 4 is a whole number. We'll call it a natural number because that's what we've been using. Is a natural number. Great. Okay. It's a natural number. Is 12 divisible by 5? No, right? And the reason why, it also has to do with factoring. I could set up the same idea. I'm just going to set it up right over here so we can see it. I could say 12 divisible by 5. No, well, I can factor the 12. You know what, I can even factor it even more if I wanted. I could write it as, instead of 4 times 3, I could write it as 2 times 2 times 3, right? We see that. And this is all over 5. All of these are prime numbers. It's as far as I can go, and there's nothing I can sort of cancel, right? I can't get rid of that 5. This 5 is sort of stuck here. If you plug that into a calculator, you're going to get 2.4, otherwise known, right, as 2 and 2/5, right? These are all the same things. This is all equal to 12 over 5. And, right, these are not natural numbers. These are not whole numbers. Okay, so this is what divisible means, what it means to be divisible. Let's keep going. The same way that hammering is a tool, factoring is also a tool. And we're going to see how we can use factoring to really make some incredible arguments. So for the rest of the lesson, we're going to be making arguments about even and odd integers, so even and odd numbers. So first off, what is an even number? Well, I'm sure we have a lot of examples, right? So for example, 6 is an even number. Yeah, sure. What else? Maybe 8 is an even number. Maybe 14 is an even number, right? And I'm sure you can come up with a bunch of other even numbers. Let's just take these 3 examples. What makes them even? So another way of thinking about even is we can interpret even as divisible, right, by 2, right? That's what even means. You can sort of divide it in half, right? And you can evenly divide it in half. That's what that word, right? Evenly divide. It just means that there's no like remainder. You don't get a fraction or something like that. And if we just take our 3 examples here, our 6 and our 8 and our 14, they are all even numbers for sure. If it's divisible by 2, it means that the same thing as having a factor of 2. Okay, having a factor of 2. And so 6, we can rewrite this as 2, right, times 3. 8, we can rewrite this as 2 times, what, times 4. 14, we can rewrite this as 2, right, times 7. And in fact, any even number you want to plop in there, we can rewrite it as 2 times whatever, right, 2 times my foot. It doesn't matter what it is. And because we can rewrite it with a factor of 2, That's what it means to be divisible by 2, right? And so that's why these two statements, being divisible by 2 or having a factor of 2, they're not saying anything different. They are identical. So if we want to say in general, because in math we like to generalize things, if we want to say, how do I write any even number? Any even number? How do I write that? And the answer is, just looking at this pattern, it is 2 times whatever, right? 2 times something. But it doesn't really matter what goes in here, right? This could be anything because we have our factor of 2 out here. Well, if it could be anything, let's use a variable because it doesn't matter what it is, right? It could be any number. So instead of 2 times 7, 2 times 4, these are particular numbers, let's do 2 times x. So just to clean this up right here a little bit, we're saying that any even number can be represented as 2x, 2 times x. Okay, how can this work? Again, not to go too much into it, but let's say that I know that the number 22 is an even number. And what it means is I can rewrite that as 2 times 11. So that's 2 times x when x is equal to 11, right? Or for 14 when x is equal to 7, right? So this x is a variable. It can take on any different number that we want it to. Great. So we can rewrite any even number as 2 times x. This is one way to represent any even number. Awesome. What about odd numbers? Well, odd numbers, let's just take our even numbers here, 6, 8, 14, and, well, I know that 7's an odd number, right? There's all kinds of odd numbers, right? I know that 9's an odd number, 15's an odd number. So what makes an odd number odd, right? Well, we could summarize it, an odd number, as not divisible by 2, right? Not divisible by 2. So that's how it's different from even, right? All natural numbers are either even or odd, okay? And we could say, oh, it doesn't have a factor of 2, right? This is all correct, but let's take a look and see if we can find, just the same way we did here, we found this like expression for any even number. Let's see if we can find an algebraic expression for any odd number. Okay, so we have our numbers 7 here, just as examples. These are examples. You could have any numbers here, any odd numbers. 7, 9, and 15. And I chose these examples purposefully because you'll notice they're just one more than the 6's, right? Than the numbers over here. So 7 is one more than 6. 9 is one more than 8, 15 is one more than 14. So let's see if we can actually use that pattern, knowing that these are all odd numbers and these are all even numbers. So 7 is really, I could rewrite that as 6 plus 1. No magic here, right? 9 is 8 plus 1, 15, 14 plus 1. We all agree? Okay, fine. Let's do a little more. Let's go a little further because the 6, remember, we already know that the 6, I can rewrite that as 2 times 3. The 8, I can rewrite that as 2 times 4. The 14, I can rewrite that as 2 times 7, right? We already did that work, right? So that takes care of my 6, my 8, and my 14. And then all that's left is this plus 1 here. Plus 1, plus 1, plus 1. So do we agree that one way that we can rewrite 7 is 2 times 3 plus 1? We can rewrite 9, 2 times 4 plus 1, 15, 2 times 7 plus 1. So in general, can we think about a way, how could we rewrite any odd number, right? How could we do it? Well, let's see, what do they all have in common? They have this 2 here times something, right? They all have a 2 times something, 2 times something, plus 1, plus 1, plus 1. So we can rewrite any odd number as 2 times something, I'll put parentheses here, plus 1. And again, this idea of that something, if we say it could be any number, it doesn't matter, right? There's nothing special about the numbers 3, 4, or 7. Well, we can use a variable here. So any odd number, we can call it 2 times x plus 1. And let's just make it nice and clean here so we have something we can box. Any odd number is 2x plus 1. Okay, so that's important. And any even number, we can represent it as 2 times x. Now again, there's nothing special about the variable x in these expressions. It could be a variable a or b or k. It doesn't really matter. What matters is that this variable could take on any number. And it doesn't matter, as long as this variable is a whole number, right, a natural number, then this expression will be even and this expression will be odd. Okay, so we did a lot of work to be able to say that any even number, we can write it in this way, any odd number, we can write it in this way. So let's take a look at this think, pair, share. If you add any two even numbers, is the sum, what you get when you add them, is that sum always even? And how do you know? So take a minute to think about that question. Is the sum always even, and how do you know? So if we're feeling like we have a lot of energy, we could say, okay, no problem. If we add any two even numbers, so let me just start adding even numbers. So let's do 2 is an even number. 2 plus 8 is 10. That's even, and that's even. So yes, that works. Okay, let me add another two numbers. Let's add 14 plus 56. That's going to get me 70. That's even, that's even, that's even. They're all even. So that one works, right? Okay, let's keep going, right? So you could certainly do this as long as you wanted to, right? And you would never run out of numbers to add, right? But the question is asking, if you add any numbers, is it always even? Okay, so we cannot say that it's always even with this sort of an argument of, let me try this example, let me try this example. You may try 100 examples. You could fill up this page and all the pages in your house, right? You could fill them all up, and maybe there's 100, 1,000, 10,000 examples where it is true that even plus even does equal an even number, right? But for all we know, if you just tried one more example, you'd get an odd number, right? Who knows? So this is where we really see the power of this being able to express divisibility algebraically and being able to reason with factoring algebraically. Because the only way that we can approach this problem, this is a proof, this is an example of a proof, okay? The only way that we can prove this pattern that when you add two even numbers, you always get an even number is through using our expressions. Okay, so what does this look like? Let's take a look. So here is our proof. So we're going to build this proof by starting with an actual example. Okay, so we're going to start with an actual example just to sort of make sense of everything. 22 plus 16. Are these both even numbers? Yes, they are. Okay. And just like we did earlier in the lesson, we're going to factor each one. We're going to factor a sum. This is 2 times 11, right? And this is 2 times 8, right? And so I'm rewriting this. I can actually rewrite this as, right, 2 times 11 plus 8. And nothing has changed, right? So I want to call your attention to the fact that this right here is an even number because it's 2 times something, right? That's what we said an even number was. So is this one. It's 2 times something. And what I ended up with is 2 times something, okay? So this right here is a nice example that we're going to be able to use as we construct our proof, right? So one question for you is, did the numbers 11 and 8, right? They were in here, but did they play any role in reasoning that this sum was an even number? No, right? They could have been any old numbers here. They were just hanging out, right? Sort of for the ride as we sort of factored and then factored some more, right? So our proof is going to start with that idea, and we're going to say any even number. Well, here's one even number. 2a, right? Remember I said before, this x, it doesn't play any role, it's just a variable. So I can say 2 times a, that's an even number. If a is a natural number, right, what we were talking about, a whole number. Great. I'm going to add another even number. Well, 2b, right? This is any even number. And this is any even number, right? So this is we're allowed to use these expressions to represent any possible even number. all of them. So what that means is that we don't have to worry about, oh, did I miss an example, right? Because this is representing any even number we want. Okay. So the proof, we say, oh, this word proof is scary. No, it's just one line, and this is the line. It's basically just factoring, right? So 2a plus 2b equals 2 times a plus b. The exact same thing, right? We did over here where we had our 11 and our 8, right? A and B are playing the same role as 11 and 8 in this proof, right? And the key idea here, right, we want to say, is the sum always even? We can say it is because this sum right here, this is the big key idea, this sum right here is 2 times something, right? Right? And that's it. That's what an even number is. Any even number is 2 times whatever, okay? So this even number is 2a. This is an even number because it's 2b. And since it equals 2 times something, it doesn't matter what a plus b is, we know that this whole expression, we don't know what number it is, right? But we know that it is also any even number. So that's our proof. This is it right here. If you add 2 even numbers, is the sum always even? Yes, because when I add any arbitrary 2 even numbers, the result is something that I can write in the form of an even number, right? So we talked about form a little bit in the last lesson. So here we see form again. We can write it as 2 times something. Great, let's keep going. All right, we just have one more problem today. So example number 2. When you add any even number and an odd number, so this could be any odd number, or just an odd number, is the result even or odd? And so we can definitely try an example. We'll try an example to say, do we think it's even or odd, right? We can use examples to say, well, I think this is the answer. I think this makes sense. But then we have to create a mathematical argument to support our claim. Okay, so first off, let's think of an even number. I don't know, 6. Great. Let's think of an odd number. I don't know, 11. Okay, so this is an even number. That's an odd number. Say 6 plus 11 is 17. Okay, so 17 is an odd number. So it seems that when I do even from this example, so this is an example, it seems that when I do an even plus an odd, the result is an odd number. Okay, now we know how to do this. We know how to create a mathematical argument to support our claim, and we're going to use our algebraic representations of even and odd numbers. So we know that any even number, I can rewrite it as 2 times a. Any odd number, I can write it as 2 times b, right, plus 1, right? And again, this a and the b, these are variables. I could just as easily have said an even number is 2x and an odd number is 2y plus 1, right? These variables are just, they're a placeholder for any other natural number, any other whole number, okay? Just want to highlight that before we move on. So we have this situation where I have an even number. So let's highlight it, right? This is our even number, and this right here is our odd number because that's how we write even numbers and odd numbers. Right? Evens are divisible by 2. They have a factor of 2. Odds are not divisible by 2. Okay? And we're going to add them together, right? And we're going to say, what do we get? Okay? So here, if I add it together, I can rewrite this. I don't know what I get. So let's just rewrite it all together, right? We have a lot of algebra. Let's just copy it down. So it's 2a plus 2b plus 1. Okay? So does this expression, the way that it's written right now, does this look like anything of the form that we've seen, right? So our 2 forms so far have been like 2 times, I'm just going to put a box here, okay, so we don't get caught up in the variable names, right? This is an even number, so if it's 2 times whatever, we can call it even, and if it's 2 times whatever plus 1, we can call this expression odd, okay? So what we have written here so far, it doesn't look like either of these possibilities. So let's manipulate it a little more. Let's rewrite it a little more. And I see here that I have a nice 2 and a nice 2. And I can actually just look at this part of the expression, and I can do some factoring there, right? I can rewrite just this part of the expression as 2 times a plus b. And then I still have my plus 1, so all right, let's just write it down, plus 1. Now, does this form help us see what kind of a number we're dealing with? You bet it does, right? Check it out. It is indeed an odd number, right? Just like we said, oh, okay, we think it probably, when you add an even odd, you probably get an odd number, right? But the way to show it, to prove it, is by rewriting this expression in a form of 2 times, I don't know, whatever, right? This is anything. 2 times anything plus 1, right? That's what we did. So by being able to rewrite this whole expression as 2 times a plus b plus 1, we can prove that you will always get an odd number because we've rewritten it in the form of an odd number. So this is the form of any, right? Of any odd number. Okay, great. So in your classwork, there are a few other proofs, arguments that you can make, legitimate arguments that you can make now that we have an understanding of what factoring is and an understanding of how to algebraically represent different types of numbers, in this case, even numbers and odd numbers. This right here is sort of just a first glimpse, an introduction into a beautiful world of algebra and algebraic proofs where you can really make sense of some kind of incredible number patterns just by rewriting things algebraically and then seeing what kind of things we can do to these expressions. For example, factoring, right? So I hope you enjoyed this and stay safe.